Well, many thanks to Jan and Benoit for inviting me here. It's a big honor to receive a doctorate without doing any work for it. And I encourage all the students here doing their doctorates not to follow my example. But what came with this honorary doctorate was a challenge. And the challenge is to deliver an impossible lecture. The lecture is supposed to combine describing Eames and Africa and the incredible opportunity ahead in Africa, as well as the universe and the incredible opportunity ahead of us as humankind to understand this wonderful universe we live in. So they challenged me to find an exciting title, and this is the best I could do. Marvellous, of course, Marvel Comics was the origin of Black Panther, and I hope some of you have seen the movie, and if not, you will see some today. And Wakanda is the name of a fictitious name of an African country, which you'll see what it's like. So I should begin by emphasizing that Eames is the product of many people. I was just the lucky person to have the original idea, but the reality is due to contribution of many amazing people. And so here you see Thierry Zomerhoen. He's the president and CEO of Eames. He was a street kid for 5 years of his life in Benin, and he was rescued from the streets, and he took 3 masters, ending in an MBA at McGill, and he led the expansion of the network across Africa. Yusuf is here somewhere. Where is Yusuf? Maybe he disappeared. There's new technology being developed. But Yusuf is head of the Next Einstein Forum, which is Africa's largest scientific gathering, happens every 2 years. And I want to especially mention 3 new professors at Eames. Wilfred, professor of epidemiology, Mustafa of machine learning and AI. Google is funding a new research center in Ghana it's the first in Africa. And over here is Mustafa Fall from Senegal, is one of Africa's leading mathematicians. So these are all incredible people who have built Eames collectively. So I want to start by telling you a little bit about myself, who I am, why I started Eames, and that begins with this. So I was born in South Africa at a time when the anti-apartheid struggle had reached a fever pitch. And so on the left is my mother, Mary, giving public speeches against apartheid. And for her trouble, she was put in jail for 6 months. And I had to go and live with my grandmother. Over here, this is my father, Ben. And you may recognize the person down here. The picture's not very good, but maybe from his stature you can tell who that is. Anybody know? Mandela, Nelson Mandela, thank you. And so my father was put in jail actually he was put in jail later than this. This was the treason trial, but they were all acquitted because the ANC had better lawyers than the government. But later on, they got my father anyway. In 1963, he went to prison for 3.5 years. So that was my roots. What I learned is that you need to believe in your ideas, even when you're against impossibly greater forces. If you hold true to your ideas, eventually the world will change in that direction. So that's me. I'm not cooperating with the photo. And this is what I was reading. So that's my qualification to talk about comics. This was a comic at the time. Turok is a bit of an unusual name, and I have no idea why it was used in this comic. But you see, Turok is not afraid to fight dinosaurs. And over here, even more fierce dinosaur, this one with some special weapons. And so I was raised in that spirit.
The Black Panther has been the protector of Wakanda for
This
generations.
is Black Panther.
Now it is time to show the outside world who we are.
The revolution will not be televised.
Everybody think they know me now. Don't be scary, cause we own now. We own now.
I have seen gods fly. I've seen men build weapons that I couldn't even imagine. I've seen aliens drop from the sky.
Yeah.
But I have never seen anything like this.
Let's go. We are home.
My son, it is your time.
Show me my respect and bow down.
You get to decide what kind of king you are going to be. Don't freeze.
I never freeze.
The revolution will not be televised.
We only getting started now, cause we own now. Everybody think they know me now, cause we own now. You and I'm my homie, cause we own now.
What happens now determines what happens to the rest of the world.
Okay, so that's Black Panther. And I love that line at the end, spoken in Nelson Mandela's accent, by the way, which says, what happens now determines what happens to the rest of the world. And that is indeed true, because what happens in Africa will very likely determine what happens to the rest of the world. In Africa, as you may know, it's the youngest continent on Earth. 60% of the population is under 25. And that comprises some 800 million people. So there are 800 million young people in Africa today. That's more people than in the entire continent of Europe, which is 740 million. So Africa's a young continent, lots of people, lots of talent, endless talent and aspiration and fortitude. And what happens to those young people is critical to the future of Earth. Either they will be a disaster if they're unemployed, or alienated, or become recruited by extremists, or there will be opportunity for them. And they will be the future pool of talent. Africa is the greatest untapped pool of scientific and technical talent in the world. And that was the motivation behind starting Eames. Now, before getting into that, you have to realize that mathematics itself, like humankind, originated in Africa. The oldest mathematical artifacts are all from Africa, and the concept of numbers and counting originated in Africa. This is one of the most important historical artifacts in the world, yet it is seldom publicized. So the Shango Bone, found in DRC, just near to Uganda and Rwanda, it's a single object, but these are the two sides of it. And in fact, I have a copy here in my bag. And if people want to have a look at it, this will give you an idea of its size. That's the Shango Bone. And it's really a beautiful object. It has groups of notches, and if you count the groups, it represents all the prime numbers less than 20. And if you add up the notches on one side, you get 60. And if you add the notches on the other side, you also get 60. So they clearly knew what they were doing with numbers. At the end of the bone, you can't see it well in the picture, but you can see it in this imitation. The end of the bone is a quartz crystal embedded in the bone. So clearly it was a kind of writing instrument. And I think of this as a 20,000-year-old office tool. Okay. Somebody had an office and they were counting and making records in Africa a long, long time ago. And why is that important? Because our modern world is built on mathematics. Without numbers and geometry, we wouldn't have this theater. We wouldn't have the concept of money or trade or finance or anything. So the key intellectual ideas originated in Africa. Now, where have these ideas led? Okay, as I say, they've led to all of modern technology and science and every device we rely on today. But this journey of discovery based on numbers and mathematics and science is, we're just at the beginning of it. And so now I'm going to transition into our understanding of the universe. And today there are really incredible discoveries being made, one of which I'm about to show you. So you may know that a couple of years ago, the LIGO experiment, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. These were predicted by Einstein 100 years ago on the basis of physics principles and mathematical equations. And one of the greatest experiments, certainly the most sensitive experiment ever designed, eventually detected them. And that won the Nobel Prize. But even more exciting and somewhat little reported, last August, the LIGO Observatory detected gravitational waves from the following event. So who knows what that is? Those two objects are giant atomic nuclei. You probably know that every atom has a nucleus, which is much smaller than the atom, and it carries all the positive electric charge in an atom. But imagine an atomic nucleus that is 3 kilometers across. Okay? That's one of those objects in the picture. And what is it called? It's a neutron star. Okay, so a neutron star was predicted from pure theory in 1940s, 1950s. Neutron star is allowed to exist. It's just a giant atomic nucleus, which is held together by its own gravity. And the gravity is so strong that all the protons, when you compress them, turn into neutrons, and it becomes electrically neutral atomic nucleus. And it's a huge object. So what happens if two of these giant atomic nuclei orbit each other? When they orbit, they emit gravitational waves. The gravitational waves carry away their energy, the kinetic energy, and the two neutron stars spiral inwards and merge. When they merge, a vast amount of energy is released. That's essentially nuclear fusion. You're fusing these two giant nuclei, and all the energy involved in the nuclear force is released. It comes out as in the form of electromagnetic radiation or gamma rays, and that drives this massive flare. And the flare is like a big spray, and it sprays nuclear matter throughout space, and the nuclear matter is like a fluid, and it's sprayed out in droplets. And the droplets are atomic nuclei, and they are the heavy elements. And by the way, it was discovered just over a year ago that this was the origin of all the heavy elements in the universe. We didn't know this before. So when you did chemistry at high school, you learned about all these elements, and I bet your teacher never told you how they were formed. And now we know. So hydrogen and helium were formed in the Big Bang itself. But all the intermediate elements were mostly formed in exploding massive stars. And then the very heavy elements like uranium and platinum and gold, these were a mystery. Until 1 year ago, when the collision of two neutron stars was formed. And why do we know this? Because when LIGO detected the gravity wave signal, it sent a warning to all the telescopes on Earth, look over there, okay? And all the telescopes on Earth looked at that point in the sky, and they saw the flare, and they saw the glow of the elements thrown out in the flare. This lasted for 2 weeks, and in that flare, you saw the atomic spectra of gold and platinum and uranium. And so we know that's where. So when you have a gold ring or a piece of jewelry, it came from neutron stars. Now, we know much more than that. We know we're learning about the whole universe, right? So we are incredibly lucky generation to be the one that got to map the whole universe, the whole visible universe. And here it is. This is one representation. Here's the solar system in the middle. And the scale on this picture has been chosen in technical terms. It's logarithmic, meaning it, the interior's magnified. This distance here is really 14 billion light years. Solar system is much smaller than that. But here we are in our solar system. And as we look out in space, we are seeing backward in time, just because the light we receive takes time to reach us. Okay? And the further we look, the longer the light takes. And therefore, the earlier and earlier we are seeing the universe. So as we look outwards, we see galaxies comprising trillion stars, typically, 10 to the 12 stars, and we see approximately 1 trillion galaxies, 10 to the 12 galaxies around us. So it's a very big universe, but as we look back, we see the galaxies, and look back further in time, we see this structure here called the cosmic web. This was the emergence of galaxies from the hot plasma that filled the early universe. So as we go back further, there's a strip here called the Dark Ages, and the red ring is the surface of the hot plasma that surrounds us. So in all directions on the sky, when we look outward, if we look far enough, this is what we see, this hot plasma. We cannot see using ordinary light any further because this hot plasma is very dense and opaque to light. But if we could see further, and actually we can, using gravitational waves, we can see right back to the beginning. The beginning of the universe is this ring, the gray ring, called the hot Big Bang, first understood by Georges Lemaitre, whose statue is outside. And there's this lovely quote, Georges Lemaitre was interested in the beginning of everything. So that's the beginning. It's very paradoxical because in this picture it looks like the biggest object in the universe. But you have to keep in mind that the universe has expanded since that beginning. So really this whole outer circle is identified. Let me just see. I'll show you a picture in a moment. But really this whole outer circle is actually a single point. Everything in the universe came out of one point. According to Einstein's theory, it's completely insane. Okay, but insane things are the greatest possible inspiration for physics, And that's what I spend my time thinking about. And I'm going to tell you at the end of this lecture the newest idea for explaining that insanity. This was very much in the spirit of Georges Lemaitre and Stephen Hawking, who worried about the same problem. So if we look in this picture, that red sphere which surrounds us, if we scan across it, right, for example, with a satellite, you can scan across that sphere, you can measure the radiation coming from that hot red surface, and it looks like this. So this is a projection of the sphere which surrounds us onto a plane, and here it is. So that's what came out of the Big Bang. So as we look across the sky, the average temperature is about 3 degrees above absolute zero. It's microwave radiation, like you have in the microwave oven. And so we're literally living in the middle of a big microwave oven, I don't know if we're being prepared for somebody's lunch. I hope not. But we're in the microwave oven. And what we see are these small variations in the temperature. So the universe, they're very small, let me emphasize. The average temperature here is 2.7 degrees on the sky, and then the temperature varies by about 1 part in 10,000, and that's what you're seeing here. So very, very small variations. They're very important because if the universe was perfectly smooth and uniform, no galaxies would have formed, and no stars, and no planets, and no people. But because of these variations, there was something to work on, and gravity squeezed these variations, causing them to collapse and make galaxies and stars and planets and people. So these are our ancestors, okay, these small variations which came out of the Big Bang. So I emphasize this picture has incredible symmetry. You know, we look around us, the universe is almost perfectly the same in all directions. And this pattern of variations in the temperature has amazing symmetry. Technically, we say it's translational symmetric, meaning that if I move across the sky, the pattern is statistically indistinguishable. It's a random pattern, but the statistics are the same across the sky. Synchronicity. This is, the Big Bang happened all at once, at one time. So you say, when did the Big Bang happen? Over there, as far as we can see, 14 billion years ago. When did it happen over there, as far as we can see? 14 billion years. It's synchronized. It's like the universe was a big bell, and somebody struck the bell. And the whole pattern is synchronized to an amazing degree. Now, that pattern looks a bit random, but when you're a mathematical physicist, you have a number of ways of looking at things. You don't need to take them at face value. Okay, so the first thing you do is to do what's called Fourier Transform, and people who do mathematics know that very well. Basically, you are looking at the system in its own terms. You see, there's some physics which governs the system, and it's the physics of waves. That this is like a big bell, and there are sound waves. And so what you should do is look at the system in terms of waves on the sky. And that's the Fourier Transform. This tells you the strength of the waves against their wavelength. And so the peak here in this pattern tells you that most of the features are roughly 1 degree across. Okay, it's caused by this peak. Now, where did this curve come from? So you see the red curve is theory, and the blue dots are experiment. Now, which area in science do you get agreement like that? There's only one, okay, physics. Right, physics is the most precise science, capable of making these ridiculously accurate predictions about the whole universe. Right? It's crazy. It's completely crazy. So this is the temperature of the sky. And then I was very lucky when I was a young cosmologist. I entered the field nobody had calculated the polarization of the sky. What's polarization? Well, just when you wear Polaroid glasses, you're looking at the sky, but only looking at radiation in one direction. And that's why you wear Polaroid glasses, is they tend to remove the reflected light, because that tends to be of one particular polarization, so the glasses are invented to remove that polarization. So the question is, if I looked at the sky with polarized glasses, polarized one way or the other way, would I see the same pattern? The answer is no, it would be different. The difference is the polarization of the sky. With my students, I calculated this in 1994 for the first time. And here is our theoretical prediction, the red curve, and the blue dots are the data. And in this curve, see, when you fit, there are some free parameters, which I'm going to tell you about in a moment, but all of the parameters can be fixed from this curve. When you fix the parameters, there are no free parameters in that curve. It's absolute prediction. Okay, it was made before the measurement, so we didn't cheat. We published that curve, and at the time, the experimentalists said, it's too small, we'll never measure it. You see, this is micro Kelvin. This requires measuring to, let's say, an accuracy of a few parts in 1/millionth of a degree Kelvin. Right? It's ridiculously accurate. The experimentalists said it's impossible. And 10 years later, they were doing it routinely. So the one rule of life I've learned is never believe experimentalists. They can always do much better than they know. The other rule is never believe a theorist, because 99% of the time they are wrong. The theorists, it's true. Probably both of those. And certainly this one. So most of the time the theorists are wrong, but actually it doesn't matter too much if you're a theorist, because tomorrow you'll have a different idea. Okay? And the errors will be forgotten. The real discoverers of truth, in my view, as a theorist, are experimentalists. I mean, theorists are there to provoke and encourage and inspire and challenge, but only when we actually see what is in nature, and we do it carefully, and we repeat and repeat and repeat until we're 100% confident, then we know. So this is an amazing story in the history of science, that we foresaw what the universe would look like, we made the measurements, and it does look like that. So the big question, what are these fluctuations? How did they originate? What caused those variations which gave rise to us? And this is the best answer we have. They are quantum mechanical in origin. And those of you who've studied physics have looked at the double slit experiment. It's a deeply paradoxical experiment. You send light through a slit, and we discovered that light is like a wave, like waves on water, waves on the surface of a pond. And waves have this property that they interfere. So the wave pattern has minima and maxima due to constructive and destructive interference of waves. But the weird thing is that when you actually measure light arriving at a screen, light is never seen as a wave. You never see waves. What you see is particles. Okay, when light arrives at a screen, it does it as particles. This is called the wave-particle duality of quantum mechanics. Now, when you hear the word duality, you should realize, you should interpret it to say, we don't understand. Okay. That light is both a wave, it travels like a wave and interferes with itself like a wave, but it arrives as a particle. And we say duality because we have no idea why it does that. Okay, very, very strange, and it's one of the puzzles of quantum mechanics. But it's due to that duality that when you see the particles, they arrive at the screen in a manner governed by the wave, but in actuality randomly. So the wave gives you the probability of seeing a particle. So at the most intense parts of the wave, you see more particles. At the least, you see fewer particles. But the actual position is random. So quantum mechanics is a statistical theory. It only makes statistical predictions. And this pattern you actually see is random. And we believe the randomness on the sky is just the same. Okay, and there are very good reasons to say that the nature of this pattern, the statistical character of it, is quantum mechanical. So somebody probably taught you in school or university that quantum mechanics governs the very small, and classical mechanics governs the large, like automobiles or buildings. But that was wrong, because the largest things are apparently quantum mechanical too. So this I've showed you a picture of the universe in space, and now I want to show you the picture in time. So we sit here 14 billion years after the Big Bang. As we go back through cosmic history, we see many features. Let's start over here. So the entire universe seems to have originated in a brilliant ball of light, which is no more than a few millimeters across, extremely dense and expanding extremely fast. And the time we would put on that is 10 to the minus 43 seconds, which looks insanely small, and it is. But nevertheless, we have reasons to believe our equations actually work at that time. 3 minutes after the Big Bang, we formed the first atomic nuclei in this hot plasma filling the universe. 400,000 years after the Big Bang, the universe had cooled. You see, it expands. When it expands, it gets cooler just because the light is stretched, so the wavelength gets longer. So 400,000 years, the first atoms formed, and this is the surface, the red sphere that we see if we look out all around us. Then there's the Dark Ages I mentioned, the formation of galaxies, the cosmic web in the other picture. And at late times you see this funny feature that the universe begins to grow faster at late times. And that's only a discovery of the last 20 years, that the rate of growth of the universe is accelerating. And that is due to something called dark energy. This is what we can see. So we live here. If we follow light back, then we're seeing on this surface the red sphere that I showed you before. And then this is why the gray circle is actually at zero size. It's a point. It's not really a sphere. It's because space itself shrinks as we go back in time, as you see in this picture. And so the whole universe came out of a point in Einstein's theory. And as I mentioned, gravitational waves, the same phenomena that we use to see those neutron stars, enable us, in principle, to look at the Big Bang itself. And right now, people are designing telescopes using gravitational waves to see past the red sphere to the gray circle, and they will be able to test any theory of how the universe began. So one of the kind of miracles of the universe is this is all accessible to us. There seems to be no barrier to us understanding the whole thing. Now, a few numbers in this slide. The important thing is only this number, which isn't a number. But how complicated is the universe? Okay, so my claim is that the universe is one of the simplest things in the universe. Okay, it's a paradox. When you look on large scales, the universe is stunningly simple. Okay, so imagine I'm trying to describe some system using mathematics. Usually I need to input some numbers, maybe the mass of the system, the velocity, the various properties of the components of the system. So let's ask the question, how many numbers do I need to specify the state of the universe on large scales? The state of the universe which emerged from the Big Bang. How many numbers do I need? So of course I need all the laws of physics, right? Electromagnetism, gravity, nuclear forces, and so on. I need all those laws, but I also needed numbers to describe the condition or the state of the universe. And it turns out there are only 4.5 numbers. So if you know all the laws of the universe, in fact, in a sense, it's only 3.5, as I'll describe. But there are 4.5 parameters in cosmology. I'll explain the half. Cosmologists can't count, that's notorious. But the half, I'll explain why I call it half. There's a famous book, by the way, called Just 6 Numbers, which describes the state of the universe, but that's a cosmologist who can't count. And the 6 is wrong, it's actually 4.5. Okay, so there are some numbers about the universe that are unimportant. Okay, one of which is the age of the universe, about 14 billion years. Well, tomorrow it'll be 14 billion years plus 1 day. So that age changes. Okay, so there's no particular meaning to that number. It's not a fundamental parameter, it's just where we happen to be. Similarly, the temperature of the universe, 2.7 degrees. Tomorrow it'll be lower. When the universe is twice as big, that number will be half as big. So that's not a fundamental number. The expansion rate, how fast the universe is growing, that's also changing with time, so that's not a fundamental number. There are 3 fundamental numbers describing what is in the universe, okay? The different types of energy. So first of all, we have the radiation, which I've already shown you, the picture of the radiation. And the only thing that matters is the energy and everything else relative to the radiation. So in particular, the number of nucleons. A nucleon is a component of a nucleus. So atomic nucleus is made of neutrons and protons. And you can just count how many nucleons there are. Number of neutrons plus the number of protons. So the number of nucleons per photon is roughly 1 in a billion. So when you look at the universe, it's got 1 billion times more particles of light, those flashes which appeared on the screen, than it has particles making atomic nuclei. That's a fundamental number which theorists like me have to explain from physical principles. Secondly, there's dark matter. Let me see if I don't have a picture of dark matter. But dark matter, I'm glad you laughed. It's a funny thing. There are pictures of dark matter, okay? To see how you can see dark matter, ask yourself, how can I see water? You see, water is invisible. I mean, it's transparent. Doesn't emit light. Whatever comes behind the water, just the light comes through. How can I see water? Well, it's easy, because when the water fills a glass, it bends the light, and the images behind the glass are distorted, right? If you're sitting in your bath, okay, and you hold your fingers up to the light, if they're wet, they will have drops on the end, and in each drop, you will see an image of the bathroom. Okay, and that phenomenon is called lensing. And so dark matter creates gravity, which actually lenses light. And we see both those phenomena. We see distortion of galaxies. We see multiple images due to the lensing created by the dark matter. I don't have any pictures, but you can imagine that it's possible to see invisible things simply by their influence on the light. So we can measure the dark matter very precisely to 2% accuracy now. And we know that dark matter exists in the universe in an amount that is 5 times by total energy, there's 5 times as much dark matter as ordinary matter. And this dark matter is very important. It holds galaxies together. The gravity pulls the dark matter in, and the ordinary matter lives inside this cocoon, if you like, of dark matter. The most mysterious is the dark energy. Dark matter and dark energy. What is dark energy? So dark energy is wonderful stuff. If you had no knowledge of the world at all, apart from the laws of relativity, okay, and somebody said, what is the simplest kind of matter possible? The answer would be dark energy. And so dark energy has the property that it is the same everywhere in its density, and that never changes. It is the same for all time, that never changes. And if you move relative to dark energy, it looks just the same. It's not like ordinary matter. If I throw this object at you, it's going to cause some problem to you. I cannot throw dark energy. It has no meaning. Its motion, it cannot move. It's just the same everywhere and for all time. That defines dark energy. So it's a wonderfully simple material, which only is governed by one number ever, and that's its density. And the dark energy is 70% of all the energy in the universe today. The energy of everything else is diluting because the universe expands. The dark energy is not. Dark energy is fixed for all time. So in the far future, we will have only dark energy, and all the stuff we're made of will become diluted away by the expansion to nothing. So the future is dominated by dark energy. So these 3 numbers describe what is in the universe. Then we have the variations I showed you. What governs the fact that the universe was not perfectly uniform across space as it came out of the Big Bang? So there's an amplitude of the variations. That is the number I told you, about 1 part in 10,000. The density or the temperature varies from one place to another. And there's a small technical... so these variations, again, ask yourself, if I'm going to throw down a pattern, a random pattern of variations, what is the simplest possible pattern I could throw down? So the first thing any statistician would tell you is the normal distribution, okay? And usually that's wrong. Normal distribution never really applies in the real world, except for the cosmos. Okay, the universe has a very, very precisely normal distribution of these fluctuations. It's technically called Gaussian random noise. People have tried to detect deviations, and they have found none. So it's really very simple, and this is related to its quantum character. Secondly, you can ask, how big are the variations comparatively on different scales? And the universe came out of the Big Bang with the simplest possible pattern, which is called scale invariant, meaning that the level of variations on 1 millimeter equaled the level of variations on a light year. Okay, just the same level. That's perfect scale invariance. So extremely simple pattern with a small correction, which is this number, the tilt. It's about 3%. It says that the variations are a little bit stronger on large scales than on small scales. Okay, that's why I call it half a number, because they're really a small number. Okay, you would be very accurate if you set this number to 0. You have a very accurate description of the universe to about 3%. That's it. There is no evidence for any other numbers in the universe. Okay, we need standard model. That means all of normal physics, electrons, neutrinos, protons, neutrons. That's a given. That has some numbers in it. But for cosmology, you only need 4.5 additional numbers. So that makes it a great field, right? Because somebody has to explain these numbers, and there's not much work to do. Okay. To describe the whole universe, quite simple. Much easier than biology. Very much easier than financial mathematics. Okay. Financial mathematics cannot be described accurately using mathematics. That's why there are financial crises, because the models don't work, right? And we really don't know. And psychology, impossible. Okay? So even to describe one bacteria and what it will do is impossible, according to modern science. We don't know how to do that. We can't build a mathematical model of a bacteria which predicts accurately its behavior. But the whole universe is a piece of cake. It's really strange. Okay, I'm not lying. That's the way nature is. So there are a whole number of other numbers. I won't describe what they are. They're all consistent with 0. So there's no evidence for anything more complicated. Now this is the standard model. I've mentioned the standard model of physics. This is what it contains. It contains particles called quarks. These are the components of atomic nuclei. There are leptons. One of them is the electron. Some other copies of the electron, and neutrinos, very strange light particles. Then there are forces. This is electromagnetism, gravity, and nuclear forces. And then there are rather mysterious right-handed neutrinos. And we know these ones exist. They're very heavy, so you cannot make them at a particle collider. But we know they exist because the light neutrinos are almost but not exactly massless. And their tiny masses are believed to arise because the light neutrinos mix with the heavy ones as a quantum effect, a small quantum effect. So that's everything. There's the Higgs boson here, discovered in about 5 or 6 years ago at CERN in the biggest ever experiment. And the Higgs boson is kind of at the heart of particle physics. And then there's gravity, force of gravity, which ties everything together. Okay, so that is all known laws of physics. Okay, it's really a very simple subject. Okay, I promise you. Okay, so our universe is amazingly simple on large scales. That's the main message. But it's also very deeply puzzling. It has a singular past. It came out of a singularity. This point, which everything came from, is what we call a singularity. It's infinitely dense matter, infinitely hot, and infinitely localized at a single point, the whole universe. There's dark energy. What is this stuff? Why is it there? Why is it 70% of everything in the universe? Dark matter, what is it? I've actually already given you the answer, but I'll explain a bit more later. Why is there more matter than antimatter in the universe? We're all made of matter. The laws of physics allow antimatter. It's an opposite form of matter, and I'll speak a little bit about that. That was essentially this number. That describes why there are more neutrons and protons, why there exist neutrons and protons in the universe, but no antineutrons or antiprotons, even though they're allowed by the laws. And the perturbations or the variations. So they're these basic mysteries which we have to solve. So let me just tell you, the new explanation for the dark matter, only recently proposed, is that it's made out of these right-handed neutrinos, these very heavy particles. We know they exist, but with recent insight, we can now see a very natural possibility that they are the dark matter. It's easily the simplest explanation anyone ever proposed. I think it's more likely to be true than any other explanation. Now, I'm going to tell you a little bit. So the universe is amazingly simple. Surely somebody's going to solve it, right? It's just waiting to be understood. It's waiting for the next Lemaitre, okay, to take the next big step forward, and then we'll say, okay, we understand the whole thing. You might think lots of people were thinking about the fundamentals of the universe, but that's not the case. Cosmology is dominated by a popular model, right? And 99% of the research is in this model, which, as I'll try to explain, I don't find plausible at all. Okay, so I diverge from the mainstream here. The mainstream does the following. You see, I told you dark energy makes the expansion accelerate. That's why that picture was growing outwards. So what theorists like me did is they said, wouldn't it be cool if just after the beginning of the universe there was a huge amount of dark energy, forcing the universe to expand really fast, okay? So that you might have a really tiny universe, but it's full of dark energy, and it makes it grow exponentially to become very huge very quickly. That is the theory of inflation. Takes its name from economics. Exponential growth is a bad thing in economics. Most people like it in cosmology because they want to grow the universe using inflation. So they postulated some extra type of field called an inflaton. We're very good at inventing names in theoretical physics. They postulated it has a lot of dark energy. This is a huge number here. And then, worst of all, they postulated that somebody gave this dark energy a lot of energy initially, and then, like a ball rolling on a hill, the dark energy decreased and oscillated here and settled at zero. So there's a lot of dark energy in the beginning, and it turned itself off, so we can't see it today. Very convenient. So you blow the universe up, and then the culprit disappears. Okay, that's the theory of inflation. It's extremely popular. It's popular because you can make lots of models. Okay, you can pick any function you like here and adjust it to fit the data. But I told you there are only 4 numbers you have to explain anyway. Why are you introducing a whole function? Okay, it's overkill. Okay, and usually that's a sign you're not on the right track, when your model has too much freedom compared to the phenomenon you're trying to explain. So this is where we are. Here's a typical plot from the Planck satellite last year. These are all the different models of inflation, these dots. And here are the observations. And you can see that the observations, as they improve, are shrinking down in this axis. I think this is the tilt, that small number, the 3% I mentioned, is basically 1 minus this number here. And this is the strength of gravitational waves created by the Big Bang. These theories all predict some strength in gravitational waves. The observations are converging on 0 for that number. And you see progressively these inflation models are being disproved one by one. The observations are just cleaning away the theoretical garbage. Okay, that's the beauty of science. Okay, but still this is enormously popular. So people are playing with strange functions like phi to the 2/3 and so on and so forth. And there are thousands of physicists working on this, but no evidence for their theories. In fact, only one theory seems to work, but there's a problem. That's the theory that actually makes no sense. Okay. So I'm not kidding you. Experimentalists actually plot a model up there that we know is mathematically inconsistent. But they want something to fit, so they put that model there. It's no good, sorry. So there's been a kind of strange evolution in physics. You may have heard of ideas of the multiverse, that the universe is not the same everywhere. It's all related to that kind of muddled thinking. The universe itself is telling us it's incredibly simple. But our theories are messy and complicated and slowly being disproved. Let's go back to Africa. Because we need an Einstein, and I firmly believe the next Einstein will be African. Okay, based on many things, one of which is sheer demographics. There are going to be a lot more young people from Africa than anywhere else. Also motivation. They have a point to prove. They are going to prove that Africans can do revolutionary things in science and technology, just as Einstein did. So here's Africa. I've explained it has a phenomenal youth demographic. And so for this reason, I'm from South Africa, and my parents, whose pictures you saw, they forced me to do something for South Africa, and I'm a cosmologist. I'm useless. What can I do? I can't build anything. I can tell you what's on the other side of the universe, but it's not much practical value in that. So the only thing I could think of is to teach mathematics with my very firm belief that this is the foundation for everything, for economic, for technology and for economic development. So we started Eames in South Africa in 2003 and welcomed students from all over Africa. I was very lucky because I wasn't involved in international development. In fact, I'm a theoretical physicist, but I have to say the most theoretical conferences I have ever attended are conferences on international development. It's very strange. Everything is conceptual and nobody wants to pin down to actually do something. Okay. People are happy to spend huge amounts of money on projects they haven't really thought through. I mean, $1 trillion has been spent on African development over about four decades, and there's very little to show for it. So I was lucky. I came from a totally different direction with a very clear objective. They're young people in Africa. They want to learn. They have ability. Let's bring the best lecturers in the world to teach them. Let's create a little hotel, and we put them together, and things will happen. Okay, it's as simple as that. Okay, and it's happening. Okay, so Eames started in 2003. We gained a lot of experience. What kind of environment works best? In 2008, I won the TED Prize. And based on that, I was allowed to make a wish in front of Bill Gates and Larry Page and Sergey Brin. These people have more money than they know what to do with. And so I was encouraged to tell them what to do with it. And so I said, my wish is that the next Einstein is African. In fact, it's not my idea. It came from a student. Like everything at Eames, the energy comes from the students. And so in 2008, we got some visibility. 2011, we opened in Senegal. This is a Nobel Prize winner, Klaus von Klitzing, and his dancing, as we do at Eames centers. They're very happy places. Ghana was 2012, Cameroon 2013, Tanzania 2014, and then Rwanda 2016. That's our president and CEO of Eames, Thierry, the street kid I mentioned. And this is the president of Rwanda, who is now the chair of the African Union. And Rwanda is sort of uniquely focused on science and technology. So recently, a couple of years ago, we moved the headquarters of Eames. Rwanda is the country in Africa most similar to Wakanda. And even in the comics, it was located not too far from there, though the comics are not very good on geography. But, but in Rwanda, we actually feel like we're creating something really new. We haven't got much vibranium yet. That's still to come. So there's a network of centers. We have 250 students every year taking masters and PhDs. We have 1,700 alumni now. 3 of them are here. I wonder if they may be in this theater. Are they here somewhere? There they are. Could you stand up? Thank you. These are our 3. Three Eames alumni at Louvain, and you will find Eames alumni all over the world, typically taking PhDs, typically very committed to going back to Africa and building up science in Africa. This is a picture from last year. This is Eames Rwanda, the current group of students. Here is Thierry again with them. Eames has certain principles. I told you that in cosmology, principles are very important, and to clearly distinguish between correct and incorrect principles. One of our principles are all completely obvious, okay, but they are principles which nobody else follows. Okay, one is talent, genius comes from anywhere. There's no point in national boundaries as far as identifying talent and giving it opportunity. So it's completely Pan-African. Every Eames student body, about 50 students, typically from more than 20 countries from all over Africa. And you have to be a truly outstanding lecturer to be permitted to teach at Eames. So lecturers are recruited for 2 or 3 weeks. They live in the same hotel with the students, and you have 24/7 learning environment, and these students work day and night, and they progress extremely well. Must mention somebody else. This you may not recognize this. The picture is not so good. This is Thuli Madonsela. Has anybody heard of her? You may be aware of Jacob Zuma in South Africa, my country, and what removed Jacob Zuma from government. Do you know who removed Jacob Zuma? She removed Jacob Zuma. She was the public protector in South Africa. She's a lawyer. She investigated corruption, wrote a compelling document that eventually forced the president from office. And now there's a much better president in South Africa. And it's thanks to her. So the reason she's in the picture is she's a board member of Eames, governing board member. And Eames operates, again, according to obvious principles: transparency, correctness, legality. Okay, and we need legal advice, business advice, to be such that the standard are the very best in the world. Nobody can ever say that Eames is associated with corruption or malpractice. This was very exciting. Last August, we launched the first ever master's program in Africa for machine learning and AI. These are probably the hottest fields in science. It pains me to say that, because cosmology is much more exciting. But machine learning and AI are really revolutionary new subjects. Cosmology, a very old subject. But machine learning and AI are really changing industry, and they have both a very amazing theoretical side and a very practical side. So Eames launched the first masters in Africa, called the African Masters in Machine Intelligence, or AMI. Of course, AMI is a French word. And people tell us that Eames sounds like aimer. And indeed, that's the spirit of Eames. It's all about friendship and love and respect and so on. So we launched AMI, and within 3 weeks, we had 800 applications for 30 places. Such is the intense interest in the field and the desire in young Africans. So these were the lucky 30 applicants on ME. 13 of them are women, and they come from many countries. I forget how many. This is the vice president of Google, and I think that is the vice president for Facebook. And so they gave $4 million each to fund this program at Eames. It's just the beginning, and this program is going to expand very, very quickly to make sure that Africa is represented in this hottest scientific field. So here's my kind of personal inspiration. Einstein, of course, incomparable success in physics. But it's worth recognizing, you know, who is the analog of Einstein for the 20th century? And I would claim the greatest leader in the world in the 20th century was Nelson Mandela. What we want Eames graduates to be is a bit of both. They have to both have the technical brilliance of Einstein and insight, but they also need to have the wisdom and the commitment of Mandela. Now, Mandela had a bit more than Einstein, to be honest. Einstein never spent 27 years in prison. Okay. But this person, who was a close friend of an inspiration of mine, he spent more than 27 years in a wheelchair. And I was so Stephen sadly passed away last year. But his only visit to Africa was to Eames. He came to Eames and he loved it. Steve and I actually, it's amazing, I could explain in more detail, had a rather similar personality to Mandela. In fact, I was fortunate to introduce them. Here they are. Unfortunately, Mandela by this point was fairly old. He was about 80. And, you know, when he was in prison, he missed the computer revolution. There are no computers in his prison. And so when he came out, he wasn't very familiar with computers and so on. And then we brought Stephen to meet him. And this person speaks through a computer. And Mandela was a bit like, whoa. You know? So kind of a Wakanda person. And you see Mandela is sitting a little bit. But soon they got on. And here's Mandela smiling happily. And that's me. And this person, actually a very important person in South Africa. Do you know who that is? Anybody know? He's one of the people who made the transition away from apartheid happen. His name is Pik Botha. He was a member of the Afrikaner government, senior minister, but he started negotiating with the ANC and he brought about, he led the change. And it was through him actually that we got to see Mandela. So, now, have I got 5 minutes? Okay. I promised you there's a simpler picture of the universe. I promise you also it is not accepted. The most interesting ideas are not the popular ones. Let me be very clear about that. If you're working on popular ideas, you're probably not doing anything interesting. Okay, I say that to all the young people in the room. So, and I hope I give you an idea what motivates me. My parents were not interested in popular ideas. At the time they went to prison, very few whites in South Africa were in favor of democracy. Okay, and they persisted and they persisted. They even went to jail. Even after they came out from jail, we were refugees. We lived in, we had to leave South Africa, otherwise they would be rearrested. And so we lived in East Africa for some time, and then we moved to the UK. And so I learned from them that if you are convinced your ideas are correct, stick to them, and in time, people will come around to those ideas. So here's the new picture. It's very unpopular, I'm very happy to say. And I honestly think it has a good chance of being correct. Okay? And I will give you, I'm giving a technical seminar tomorrow, so anyone interested, you can see it. I work with a number of students. They are here, and young faculty. How could the universe begin? Right? Sounds like a ridiculous question. Does it make sense for anything to begin fundamentally? What is before the beginning? Makes no sense, right? No, it makes perfect sense. Because in physics, the beauty is that nature is extremely economical in its principles. Nature uses the same idea again and again and again and again. That's why mathematics works. Numbers are everywhere. Everything is described by numbers and mathematical logic, the laws of physics. The existence of a law means that nature uses the same idea again and again. So here's how, instead of universe, let's go to a simpler system, a particle. Can we create a particle where there was no particle before? The answer is you can, and it's contained in this paper in 1941 by a remarkable person. The other lesson I want to emphasize actually is the people who really discover amazing things are often very strange people. And here's one of the strangest. I encourage you to look him up. He was kind of a recluse. He only published in very unknown journals. But he had this idea. So we're going to do some relativity very quickly. Relativity and quantum mechanics in one picture. Okay, so relativity, what does that mean? Well, time is a dimension, and space is another dimension. Okay, so you should think of them like height and length in this room. Those are the axes. And we follow particles in time. They travel forwards in time. They tend to travel forwards in time. And they can move around in space. So a particle, this is a typical particle. It goes forwards in time, up this axis, and it also is happening to travel in space. This person realized that according to classical mechanics, if a particle is going forwards in time, it cannot turn around and go backwards in time. The classical laws of mechanics exclude that possibility. However, the quantum laws of evolution allow a particle to do that. And he realized that. So you can have a particle that is traveling forwards in time, and then something happens, and it turns around and goes backwards in time. That's perfectly allowed, cannot be excluded for very, very fundamental reasons. Likewise, you can have a particle coming from the future, turn around, and go back to the future. Okay, that's allowed by quantum mechanics. Now, how would we describe this? Well, we are looking from the outside. We live at a fixed time. Okay, so we can't see all of time. We're just aware of this moment. So we see the world on this surface at this fixed time. What do I see here? One particle. If I look at this time, I see the same particle, but a different position. Right? It's moved. But with this particle, I see it here, at this position. But I also see another particle. I see two particles, because I see the same particle, going backwards in time. This is an antiparticle. A particle going backwards in time is an antiparticle. So the prediction of this picture is that for every particle, there must be an antiparticle. And this is indeed true, according to experiment. For an electron, there's a positron. For a proton, there's an antiproton. Neutron, there's an antineutron. So now what happens here? Well, the positron is here, the electron is here, the positron is here. As time goes forward, they annihilate. Matter and antimatter, if you bring together, they disappear and they release some radiation. Over here is the creation of a particle on this side, antiparticle on that side. So you can create particles from nothing. And the way you do it is by having a particle come from the future, turn around, and go back to the future. Then you get two particles. So this again is another picture. Here's my electron going forwards in time. Here's my positron going forwards in time. It's just the electron going backwards in time. The view on this line is the internal view, the view of the particle of itself. It sees time going one way along its line, but the external view is that the particle went back in external time, turned around and went forward in time. Okay, so this is very well established physics. We see this in experiment, we know that it's true. Here's a more detailed calculation recently by myself and students, and you see the particle going backwards in time, turning around. This is the really quantum region. You notice the funny pattern here, the interference? It's like the interference in the double slit experiment. It's when something is very quantum, you see that effect. So that was the beginning of the universe. But the universe has two sides. One on one side it's going back, the other side it's going forward. You can say this side created that side. Or equally, this side created that side. The universe created itself. Okay, different parts of the universe created other parts. I won't show you that one. That's too technical. But this we call the Cpt Symmetric Universe. It just came out a couple of months ago. Part of the universe created, literally you should think of this as going backwards in time, creating this very dense quantum, very quantum region, and then the universe emerged from that. But equally, you can have this, it's equivalent to say this side created that side. Okay? So that is the new proposal for the beginning of the universe. It has a number of predictions. We're still working them out. It explains the dark matter. We think we've solved the dark matter problem. It's right-handed neutrinos. We can calculate exactly how many were created in this picture. And all the other puzzles in cosmology, we think are, some light will be shed on them by this very simple picture. This is there because I want to tell you, to end, emphasize experiment is the final source of truth. Theorists like me are just there to encourage experimenters to test, to check. We saw that beautiful picture of these stars colliding, right? There's been a revolution in radio astronomy, and you look for it. It was announced recently. It's if you just Google this, it's a new type of radio telescope which can now scan the whole universe, provide a 3D scan, and it's discovering all kinds of things. So these are some of the people involved. This is, I was going to show a movie. Let me just see if the movie is there. Nope, the movie isn't there. Okay, but so there's a wonderful radio telescope. If you look at CHIME, you'll see what it's found. It's found flashes of light on the sky originating from the very distant universe, and a whole lot of new information is coming. There's an African component of the project in South Africa called Hyrax. This is the leader of it, and there's a piece of it in Rwanda. Okay, so just to sort of give you a 10-second view of this project, what's so revolutionary? It relates to computation and machine learning and AI and all that. These are changing the world. If you think about radio astronomy, what is it? So basically you make a big dish, right? A huge dish if you want to see a small object, and you point it at the object. So it turns out that's not necessary. That's old-fashioned and very expensive. This huge dish is tremendously expensive to build. The modern ones cost $1 billion. And moving it is enormously expensive as well. What do you do instead? Instead, you make a very cheap array of regular satellite dishes. A little bit fancy, but a few $1,000s each. Make a huge array, rectangular. They gather the information, and then you put it all in software into a supercomputer, and you focus the telescope in software. It's called a software telescope. Okay? You don't need the mirror anymore. When you do that, you're able to focus the same telescope on all points on the sky at once. It's a revolutionary advance. Okay, and the first telescope to implement it is CHIME, and they're now making enormous range of discoveries. So there's the one in Canada, CHIME, and the one in Africa, which my former student is leading. And that one in Africa has a component in Rwanda. So we're fully expecting some really amazing discoveries about neutron stars, black holes, spectacular events in the universe to be made in the next decade in Africa. Thank you. Yes, thank you. Okay.